He has a very big bio, but I will just cut it short. So Srini is co-founder and CTO of VerifWorks. He is the main developer of Go to UVM and open source UVM application, and he has more than 90 plus years of experience in DV, design, synthesis and EDA. So let's welcome Srini for the further presentation.
Okay, so good evening. Actually, we're doing it on behalf of Krishna Tottampudi, who's in Qualcomm, US, and he could not make it to this conference. So he was kind enough to give us his slot and said, you go and present it. And I also have a couple of my co-authors, Pranesh and Mani. They're not here today, but Pranesh was here this morning. So let's start with this. Some of you may know me as CVC. CVC is my one company, and VerifWorks is just another company. So it's just a new one. Okay, so this is a quick agenda for today. We have an introduction, and then I'll talk about the test layer, which is kind of the very first entry point for an RTL designers, and then you go and look for apps to automate things. And then the primary thing where Krishna really had a lot of value in this, actually this was presented at DVCon US as a tutorial. So we extracted some part of it, and then we said, let's publish it as a paper. And the register verification, I would say, is the key for many RTL engineers, at least the likes of Qualcomm. And I'll talk about that, and then we'll also talk about the waves to UVM and a checker stuff. So this slide, I believe most of you know whoever is using UVM. We just had a paper on UVM for FPGA guys, and the point is whether it's FPGA or an RTL designer and it's UVM, and you go and show him this, he'll say, okay, I'll come back to you, I'll call you back, and they never call you back. And that's really what happens, because it's so complex for the RTL designers. It's not like they are not smart. Actually, they are smarter than us perhaps. I used to be an RTL designer long back, but then I moved on to DV. Just that they have other things to do in life, right? So this is what we are trying to say. We could find ways to simplify the UVM for the primary first-time users, and then get them more and more advanced into complicated use cases. So we need to find a way of simplifying UVM, and that's really what drove me to start this thing called Go to UVM. It's also a website called gotouvm.org. You could download things from there. So for those who are starting with UVM, perhaps you know this mechanics, how it works. And it has multiple layers of components, like your driver, your sequencer, you have an agent, and then an ENV, and things like that. And then you start writing sequences and tests. And this is fairly straightforward for a UVM guy. And there are component hookups, wherein, again, please think for a moment, over as an UVM expert, think about those days when you did not learn system Verilog, OOP, and UVM. And you go and show that person, let's say 5 years back of you, and then show them that, hey, you need to do a SKU and then a name and a component, a parent. They just say, okay, this is too good for me, right? And then there are a lot of macros, and there's phasing that you need to teach them. There's a reset phase, main phase, run phase, and previous session, for example, is showing build phase and run phase. So people need to be aware of this before they can start using UVM. And those were the hindrances we were hearing from a lot of these people using it. And for those who have used long back this VMM and OVMs, the objection mechanism really creeped into UVM. It's actually a great thing, according to me. But then the way it works today, if you do not put an objection and you have a delay in your test, somewhere you do have it. If not a hash delay, but you do have a clock delay. And unfortunately, the way UVM is architected today, it would not tell you anything, and it would simply quit. It would not honor any of your delays unless and until you have an objection mechanism. Again, for those generated UVM benches, it's probably not a big deal. But again, trying to teach this to a non-UVM engineer is very difficult to go and tell them you need to write this code called phase.raise objection and then phase.drop objection. So what can we do? That's really what drove us into this. We said, okay, not all engineers are familiar with the full UVM, and this also includes a lot of academicians. For example, I was just teaching a lot of this university grads in Brazil, the same thing. And you cannot expect overnight a lot of people across the globe to pick up UVM. And with UVM becoming an IEEE standard, we expect it to go to all other places that we have never been to. That's really the idea here. So the RTL designers require different requirements. They have a slightly different set of requirements here. So they need simple wire wiggling for really quick tests. That's the first thing that I'm going to show. And then they also clock and reset propagation. This is what they want to test. The reason why we listed this specifically again from Qualcomm is they said DV guys do a lot of functional tests, but this is what RTL designers want to do as tests. You want to test for clock frequency, not the complex ones that were presented previous presentation, but just imagine you want to change the frequency a bit. Right? And simple connectivity tests, the force deposit release for corner cases, and early register tests. So I'll focus some of this into my slide deck because we have one very short time. And there are also auto-generated tests. Some of them I'll talk about the waves to UVM. So this is really what GoToUVM as it is today. It's not everything is in there, but most of it is in here. You see that there is a test layer on the left, and then there is a signal access layer, which allows you to do random fault injection. For example, you could use this for a safety verification or error injection in an FPGA and things like that, along with your regular UVC traffic. You could do that. And then there is also a register verification layer. And those are the two things I'm going to be talking today more in detail, the test layer and the register verification layer. The other ones are really part of other presentations and talks today. And there is a log predictor as well. For those who are familiar with the UVM full picture, this is a UVM RAL and this is a UVM reg_predictor. This is modeled in line of the same thing, saying, if I can predict the register contents, how about me predicting or trying to predict my log file? And again, these are required in a functional safety requirements and etc. That's where this is very applicable. And some of the apps or the template creation app, the Waves to UVM app, which I've introduced today. So just for the moment, let's take a very, very simplistic case of a FIFO. And some of you perhaps seen this slide deck in the FPGA thing. Sorry, we have reused this slide deck. But essentially, if you're an RTL designer having a FIFO like this, couple of signals, and then you want to write a sanity test. And what we provide in GoToUVM is there are two tasks that we provide. And we ask you to fill in the reset and main. And in fact, to be precise, it's only the main. You fill in the main, we get things done. You don't fill in the main, we give you a compile error. That's as simple as this. So in a case, just think about UVM. If you forgot to write anything in the main phase, nothing will run. In GoToUVM, you forget to write the main, we will actually compile error out. So you will have to fill something for us to get running. Okay, that's really what we're going to be doing. So let me show you a very crowded slide. I'm sorry about that, but very high level, what I want you to kind of highlight, we have put it as a call out in there. That's a test. That's basically a macro that says GTU test begin. And for those who are familiar with the UVM, it's nothing but class my test, in this case FIFO test, extends UVM_test. But for those who do not know it, it's just GTU test begin. And under the hood, it also calls the function new. It calls the new.string, the parent, all that stuff, name and parent, it automates. This is again, most of you know this. You could download the macro and see it for yourself. The next thing it does is the interface part. Again, that confuses a lot of people, the config DB. The config DB set and get is tricky. If you know it, you can use it. If you don't know it, you cannot use it. So we made a macro for this. Use a get wef, we will take care of that. And there's a reset, as I'm talking about, and there are other things like displays, smaller, low-hanging fruits. I'm not talking about it. Very high level. It's like your dollar display, but with all your UVM bells and whistles. And so you go and toggle the reset, wait for a few clocks, and then go and untoggle the reset, meaning set it to inactive state and come out. In this case, it's active low reset, so you reset 1 to be 1, right? Reset_n to be 1 towards the end of the reset task. Let's come to the main task. In the task main, and we just have a main display, and then we go and say, okay, let's push. Again, please remember it's a FIFO design. Okay, you can do a push and then send some data and then get out. If that's all a designer wants to do, this is all he or she has to do. It's that simple. We get it running, up and running in about 5 minutes with UVM. So, okay, so the last part of this, which hookup part, you'll have to know a little bit about this. I mean, all of the RTL engineers do this. Instantiate this in your top level and generate the clock, and then call run_test. That's really what the starting point for UVM is. And so that's primarily what the test layer in GoToUVM gives you. And the good thing is, okay, to some extent there is some code. How about we automate even this? That's what we call as an app. These are mostly TCL. Some of them are Python-based apps because the register generation, for example, is a Python-based app. But this one is a Tickle-based app. So on the contrary, if you are a strong UVM guy, you would go and build this, right? But if you're an RTL engineer who just wants to get things done, and he or she doesn't have to build this, and they don't get scared, you go and show them this, I believe they can do this. That's really what the idea is. And to take it to the further, saying, okay, I have a list of files, or I have a file called rtl.v. Can you give me this framework as a generator? Yes, we can. So we have a GUI. And again, most of you may have a script to do this. The specialty of this is, one is the GUI based. The other one is it actually hooks up your RTL, generates a system interface, Also, it connects your test, top, DUT, go to UVM test template as well as a make file. Again, no brainer, no big brainer. Anyone can do this. It's done. It's open source. Please take it. You don't want to redo this work. You could just take it and reuse it. And till whatever I have been talking so far is open source. And wherever it's not open source, I'll kind of mention it, and so that you can be cautious. But this is all, you can take it for free and use it. This let's say you want to plug into a Xilinx. We have already a plugin. Okay, this is free. So with Vivado, you click a button, you get all what I was showing you there. Okay, so that's my test layer. Believe that's good enough to use, and we also have apps so people can start using it. Let's talk about a quick app which is called Waves to UVM, and this made actually quite a bit of waves during the DVCon US, so I thought I'll bring this in here. The motivation is most of your spec does include some sort of a timing diagram, maybe few, maybe a lot. I look at APB, for example, you have 7 or 8 timing diagrams in your PDF file. Now, how about, and they are actually represented in a way that it's formal and ambiguous way to capture the timing between your signals. So how about we convert that into UVM? Again, the motivation of go to UVM is let's go to UVM with whatever we can. So this should work with all popular waveform formats. I'll show you one that's open source, which is WaveDrom. It's a JavaScript-based, JSON-based description language. It's not owned by me, it's owned by someone else. It's an Eastern European guy, great guy. Go to wavedrom.com, you'll find it. But let me show you a demo of that. Over on the left-hand side, you see there is a waveform. Let's say this is a small VL bus protocol wherein there is a read and write signal, and then there's a read-write valid signal. Okay, so you see that there are 2 signals. There is a clock as well as there is a read-write valid and then a read-write signal. So it's that simple. Let's say someone wrote a timing diagram like this, and the language that I showed you over there is a simple JSON language. You like it, you use it. You don't like it, you use your tickle, you use whatever you want. Right? There are various VCD formats and etc. But this, I believe, is fairly straightforward. And the good thing about JSON is it runs on your browser, meaning you do not have to have any tool. And the good thing about Waves to UVM is same. Since it's a JSON-based thing, you could actually, on your Google Chrome, you could click a button, get a UVM file out. Okay, so let's show you how it works. It builds on the layer that I was talking about, the test layer. In this specific case, what it does is, for each of those signals, it creates one task. On the right-hand side, you see the arrow, and then coming down, you see a drive underscore VLB write read. For those who can read it, well and good, otherwise I'm reading it for you. So there is a task that it generates, and it exactly follows the timing diagram that's already given there. And if this is this simple, why you want to write it yourself? And why not generate it, add it to your regression? And at the end of the day, all of these tasks are fork joined inside the task main. And as I was talking about the go to UVM, the main entry point for you is the main task. And until and unless you fill the main, nothing runs. And if you don't fill in the main, we compile error. Right? As for those who are kind of curious how we do it, it's a pure virtual task. So you make it a base class, a pure virtual, and the derived class must implement it. So if you don't, your compiler flag it. So that's what we did with the task main. So you must fill it, and in this case, again, it's an automated app. So take your waveform in, generate whatever you see as a source code over there automatically. Click a button, get it. Again, this is based on JSON. It's not perfect. It doesn't work for all scenarios. It doesn't support the entire WaveDrom format, but that's the idea for an open source. I'm having a couple of research guys trying to extend this for various vectors and etc. Hopefully we'll get there. Okay, so the next topic is on register verification. This is primarily, I should acknowledge that this came a lot from Krishna. He put in a lot of effort in creating these slides as well as the flowcharts. I wanted to give him the credit. I wish he was able to present here, but anyway. So in a typical environment, the registers are available either as an IP exact file, like an XML, or YAML file or something like that. So most of the teams do have this even at their RTL verification stage, even at the RTL development stage, because this is kind of considered as part of your spec. What's also true is you have a bunch of generators available out there that could read in your IP exact file and spit out a UVM register model. This is no brainer. A lot of people have done it. There are companies living out of this. There are companies acquired due to this. Some of you probably know this. And the good thing is there is now an open source tool to do exactly this. It's a Python based, done by a guy called Tudo Timmy. For those who are interested, he's works at Infineon in UK, and he has put it on the GitHub saying, hey, this is origin.py, go and do what you want. And what we did, we took that and extended it for go to UVM. So let's say, how do we use it? Let's assume that somehow either you have your VCS, RALGen or something like the ArtSet and different tools to convert your IP exact to a register model, or you do it using our open source tool. Either way, you do that. Once you have it, what do you do? Getting a register model is not the tough problem, it's solved. But what do I do with it, especially for an RTL engineer? In this case, I'm going to follow only one part of this flowchart, which is I'm going to assume that the designer is not knowledgeable in UVM. But in case they are, there are more beautiful things they can do. That's part of our other tutorial. But let me focus on, let's assume the answer is no. If the answer is no, here is where we plug in again with our go to UVM. You say, okay, since you are not aware of UVM and UVM VIPs, UVCs, your Synopsys, Denali and others, right? So what you do is you describe your protocol in an interface file and a system with like interface. And there are two tasks that are GTU write and GTU read. GTU stands for go to UVM. And then as per your config bus protocol, which I'm going to show you one small example, once you do that, about 7 or 8 tests we auto generate for you. Let me show you that. In case you are familiar with, the RTL engineer is familiar with UVM, you could also use your standard VIPs, commercial VIPs. That's part I'm kind of skipping for today. So, steps. Generate your UVM reg model from the IP exact. Generate a template. Again, we have that thing. It's not directly on the go-to-uvm.org, but it's part of a GitHub. But anyway, you could pull it out. And you may have your own script, or you could use this open source script to generate the RAL model, the register model. Then the skeleton structure has a dummy driver, and that calls the GTU write and GTU read. And for those who are familiar with the register layer, there is a driver as well as a monitor. Both are going to call these tasks. And we in fact have these base classes already done for you. They go and call this. So user needs to fill these two tasks to get going. And then you can start writing tests. Let's look at 2 slides, a little bit again crowded. So let's assume that you have this timing diagram that I was talking about. Similar to the waveform, you have a small protocol that says, if I were to do a write, put the write read signal high and then write read valid high. And again, my claim here is any engineer, any Verilog engineer could write the code over there. You do not have to be a UVM expert. You do not need to understand OOP to write this code. You could say, okay, write read is 1, write read valid is 1, put the address, put the data, wait for a clock, pull them down, right? And then we are done. And that's all what we are asking is fill it into GTU write. And the moment you do that, let's see what we can do with this. Let's look at the test. This is the beauty of this. So if I have tests, if I have a design with, let's say, 50 registers, you generated your UVM register model, push a button. Then you fill in this one, the previous one I showed you. Then you're up and running. All those 50 registers can be tested on day 1. If you can write this in 1 day, which I believe we can, right? You write this, then we can actually start running tests, real tests with UVM. You do not have to be an expert in UVM to start using this. It's all you need. And some of this actually we generate using the app as well. So you could say, I have a reg test begin. Again, if for those who look at the details, there is a GTU test begin. In this case, we use another macro called reg test begin, because the reg model will require a reg env, and that's what we call as a GTU env. Right? So the GTU instantiates the built-in drivers, monitors, and etc. So it's a fairly comprehensive stuff under the hood. And then you have a task main that goes and says, okay, this is the bit bash sequence I want to run. I have other example of the other sequence over here. If you want to do a reg access sequence, someone was asking, what if I have read-only register? You do not have to write any more tests. Do this. Again, most of it is already in the UVM. The fact is, there is a reg access sequence, there is a bit bash sequence within the UVM layer. But unfortunately, not everyone is familiar with it, especially not the RTL engineers. And with this, the 50 registers in your design can be tested in a day or 2. So that's kind of the test generation along with the registers. The next quick feature that we have is what we call as a checker library. And for those who have been tracking us, we got into the fame thanks to assertions. And we've been investing a lot of time in doing assertions-based verification as well as writing books. And one of the recent trends in assertions is to write what we call as a checker and checker, which I'm going to give you an example of. It's a new construct. Don't worry too much about that. It's just a, let's say, encapsulation for all your assertions. However, now RTL designers need ready-made, it's not a read-made, it should have been ready-made. As a ready-made checkers, they do not have the time to go and write a lot of assertions or detailed scoreboards. Right? Detailed scoreboards are way too far for an RTL engineer. They could write assertions. Let's start writing an assertion for a small design. Let's say they have a very, very simple protocol again. For those who have done any assertion, the assertions do not start if you do not have a request ACK. It's that simple. People go and say, hey, always for an assertion training, go and show a request ACK. That's exactly the example here. Request an ACK, there's something funny there. But the fun part is here. Let's say we have an int long underscore delay. You need to read the code to understand that. Sorry, it's a bit of a thing. Okay, it's a runtime delay that you could see. The long underscore delay is actually an int variable. It's a runtime variable. And then someone writes a property like this. People are familiar with assertions. They go and say request implies pound, any number is fine. But you put a long delay, which is a variable, the compiler is going to come back and tell you, look, I won't allow this. For those long timers in this domain, it's a very, very painful thing because 15 years back, we were doing this right opposite to this office, this building at Intel using Specman. So technically speaking, I don't believe there's any reason not to support it. But unfortunately, the language, the LRM, this is nothing to do with the tools, is a language that doesn't allow a non-constant delay into your assertions. Big pain for those who are looking at these configurable designs, and many of the designs are actually this way. Right? What can we do? Here is the real solution for it. You could use assertions today, by the way, or we could have done it like 5 years back. You could write a property that's, again, sorry about that setting, but you can see the full thing, but it's basically a property that uses what we call as a local variable, and you could implement that. For those who are aware of it, well and good. But again, think about an RTL engineer who wants to write a check this, and then he cannot write this code, and I believe they cannot write this code either. So what did we do? It's complex. We said, okay, let's write a library. That's called VW, that's our company name, a GTU, where delay check, and it has a checker and checker. That's kind of the encapsulation. I'm going to leave it at that. Let me show you the use case. And the code is looking very similar to what you see on the complex SVA. Is hidden under your checker. And all a user needs to do is what you see at the bottom left corner. You go and say VW GTU where delay check with a request ACK. Let's say you give it a name, instantiate the checker with your dot star, meaning connect all the guys, except for the start signal is my request. The end signal is my ACK, and my where delay is actually delay. It's just a runtime variable. And this is no magic. There's nothing really go to UVM invented here per se. All it did is, okay, this is a local variable based approach. We put it nicely under a checker library for you. So we could run simulation, and here is the two things that's going to happen. One, when the design fails, when the assertion fails, you're going to get a nice error message over there with the UVM error, so you're not going to miss it. The other problem with assertions, you write an assertion like that, your UVM error will say, I'm happy, the test is passing. Know why? Because there is no action block over there, and the built-in $error would not trigger an UVM error. And for those who are looking at UVM day in and day out, you look for a summary called UVM errors, and you get a 0, and you thought the test is passing, but actually there was a failure in assertions. It wouldn't happen with the checker library because it's all built in. There is an action block, failed action block that goes and calls the GTU or the tick UVM error, as you are aware of. It goes and says, okay, there's a UVM error, and it says the end signal did not go high after 10 clocks, and assume the delay is 10, and this could change on the fly. That's the, let's say, the failure side of it, the checker side of it. What we also do, which is very, very nice, some of our customers have given good feedback about this, this is the last line. It also has a debug hook that goes in, and by default it is enabled. It goes and says, look, you know what, you wanted at 10 clocks, but I found the ACK in 12 clocks. So it's actually pretty good in terms of it doesn't do just a check, it actually does a little more. It does a count and then comes up and tells you, you were maybe looking at 10, but I got this end signal at 12. Of course, assuming the design did toggle the ACK. So there are two things built into the checker library. One is the check itself, the bunch of assertions, as well as some debug code that goes and tells you what's going on there. Okay, so that's my last slide. I'm okay on time. UVM is here to stay, meaning you probably saw the IEEE 1800.2 update. We are looking at UVM for 5 to 10 years, maybe much longer than that. So it is going to be there, despite all your other advancements, it's going to be there. And we need to get it adopted by all stakeholders. There are lots of other reasons why someone may not adopt, but provided someone wants to do it, here is the way. GoToUVM provides a means of adopting UVM for RTL designers. And on top of which, we also have apps that makes the automation. Give you an RTL, I will give you the setup in 2 minutes. Right? So essentially, you could also bridge RTL to DV with respect to your IP exact models, the registers, the tests, the assertions, and etc. So though a lot of people think GoToUVM has been around for about 2.5 years. We had a couple of papers in the last year as well. So it was started as a test, but has evolved much more than a test. And we openly welcome us actually inviting Kunal to start donating whatever he is doing as a real world clock generator, jitters, and etc. We could add, and I openly extend that, because it's an open source, it's GitHub based, people can add their own libraries, provided some qualification we do, and then we could go and add them. And there are some apps already available there. The Waves to UVM is free. The RegGen is also free, not created by me, but someone else. And then I hopefully acknowledge them well in advance so that you all know who did it. And it's all there in the GitHub, you would see it. And the DB Create app, my team did it, it's all there. And we also have a checker library for quick checkers. And not everything is shown here. We have more coverage models in there and things like that. And not everything is extremely well documented, because we are not a big EDA company with a lot of funding. So we don't have all the energy to go and document it. We are engineers, we are bad at documentation. But live with it, or maybe help us improve. Let's do it together. Thank you very much. Any questions?
Do you plan to add coverage as well, like the automatic coverage generator?
Good. The answer was yes, we do already have some. And the checker library, we already have some coverage models for you to use. Okay. But I do not have a coverage. I mean, I could add a generator for coverage, like, are you Munjal, Mr. Munjal is, are you Munjal? No. Okay, because Munjal was presenting a functional coverage generator in the other presentation. If that is what you're asking, no. I don't have, I mean, maybe he can. I mean, it is free to open source to upload it. Why not, right? We could do that, not as a free. Right now, I don't have a plan, but I'll be open to do it.
In that Waves to UVM which you are showing in the example, is it possible to generate the protocol signals which are asynchronous to the clock?
Good question. Waves to the JSON, okay, let me come back. Wave draw, I believe you can do that, though I have not done it. Maybe it's possible. But given that the UVM is, I mean, the GoToUVM generator is clock based, strictly speaking, we cannot do. I'll be honest on that. But of course, it's a generated code. It's very readable. And again, that's an important thing. Thanks for bringing it up. You look at this code, there's nothing really fancy. Anyone can edit it. It is not a crazy, and it's really a generated code with the indentation, right? The indentation is really generated by the tool. So in a sense, what I'm trying to get to is you can go and edit it. But of course, be careful, because it's a generated code. We are really tracking clock by clock. The moment you add, let's say, 4th line add delay, everything else gets delayed. You need to be aware. It's not parallel, it's sequential code. Once you know that, you can modify it, yes. But it doesn't directly support it, yeah.
What is the size of the checker library we're talking about here?
You mean line count?
Not line count. So library means it consists of many of the fundamental checks, right?
Mm-hmm.
So what is the size of this fundamental checks?
Good question. Just to be sure, we are not replicating the OVL of the world. If you know the OVL, the Open Verification Library, that has about 32 plus or 50, 61 checkers or something like that. We are not doing any of those, because that's already done. That contains your simple checks, simple protocol, I wouldn't say protocol also, but simple checks, already about 61 of them. And none of that is part of GoToUVM. You can download the OVL, you can use it the way you want. We are not adding any of that. What we are doing is something that's a little more advanced that people cannot do, something like this. People cannot write this. This is what we are adding. Today, if you ask me, I don't know if Mr. was, but about 7 maybe. I mean, she's the author for that. How many checkers we have in the checker library? I'm not sure. The checker library, how many do we have? 6, 7?
8.
8, 6, 7, somewhere there. You can open the code.
It's less than 10, but it's very handful.
Yeah, I mean, again, we are not, please differentiate, is the checker means it could be 4 assertions per checker. We're not counting the number of assertions here. Number of checker library elements is somewhere around less than 10. Keep it there.
Okay, thank you.
In this example, integer cannot be used as an array, but can't the parameter be used?
Parameter, yes, but parameter cannot be changed at runtime. You cannot change it runtime.
Right.
Runtime you can't do, and runtime delay is what people want. And if you want that, but by the way, thanks for bringing it up. We could use this for even your elaboration type constant. You could pass a constant over here. It will still work, and it will actually give you the debug. That's another good reason to use this library. The typical assertion would only fail. It wouldn't tell you when it found it. It was looking at 12. I was looking at 10, but the design gave it at 12. Your constant or the standard assertion wouldn't tell you. A checker would tell you, provided you code it. Of course, there's no magic in there. You'll have to code it. Anything else?
Can UVM test bench, whatever created, right? That can be extended by the verifiers as well?
Yes, I mean, this is a code that anyone can be, I mean, one test.
Because you're having only two constants, resets and main, right?
Okay, good point. So okay, this is one example. We are using the entire UVM register framework right here. There is nothing that is stopping you. This is again a generated code. I believe this is fairly decently indented that anyone can go and modify it. So we are not preventing anything to be done by end user after the generation is done. So we just give you an easy way to start using it. From there, you start adding things. For example, the low power, we have an LPUVC, which is not part of open source today, but that one, we give you a bunch of power up sequences, but you could use them the way you want. We are not going to prevent anything there. You can extend it the way you like. We give you an ENV, you add things to the ENV, if you will.
So in the checker, you are also giving report that if it has the acknowledgement has not come up.
Initially we started working with the checker. Then we while debugging, I'm waiting for 10. After 10, nothing happened. I don't know. I didn't have any clue whether it happened or not. So that's when I added the message. Then we know exactly it's happening.
You need to open a waveform to see where. Okay, it told you where it did not find it. But can you also do a debug for me? Meaning without me having to dump it and rerun it. Here is a debug.
So if let's say if we didn't get act in 12, then your assertion is still active always.
Assertion has already failed at 10.
Right, but your checker is active.
That's right. Checker is
Does
active.
that has a performance issue?
Yeah, why not? I mean, it could. I mean, essentially, you have an open-ended thread. You have it for 10,000 clocks. Eventually, you will. But,
Or you use some threshold and then it will.
we could, but we are not doing it today. I mean, you could extend it.
It fails, especially number of times. It's 100, 200 times. So I don't want to look each and every instance. When this really failed, which is it a real failure or not, and when exactly it is happening, and the debug is really painful.
Right.
So we added them, then it's just jiffy.
Okay. Anything else?
Any more questions?
Thank you very much. Yeah.
You have something of training protocols in the serial training protocols, so you detect.
Sorry, come again, please.
Do you have something for serial? So you have training protocols where you just have a serial line that is toggling, and if you can have an expression that can help us.
You mean here?
Yeah,
In this one?
in these assertions.
Sorry, I didn't get your question. We'll have to repeat that.
So you can have a framing, like a training pattern or something like that, on
Mhm.
a serial line, which is
Okay.
very difficult for verification engineers to sit and look at each bit on the line and figure out
Okay.
where the pattern is.
Mm-hmm.
So do you have something like this also?
I am hearing for the first time, so no, I don't have it.
So what's
But you can add it.
Yes, we can.
You can add it. I don't have that today. But since you said serial protocol, as part of the register verification, we do provide an I2C GTU write and read. That's something I didn't talk about a lot. But in the register generation app, we also provide you an APB, an HB light, as well as an I2C protocol layer for you. But we don't do any of those pattern matching that you're asking for. We don't do that. But we could add it. I mean, you could add it. It's an open source thing.
Okay, I think we are running out of time now.
Thank you very much.
That was a nice presentation. So thanks.